Okay, so in this video we're just going to talk about some of the basics of quantum theory and atomic structure. We'll be talking more about atomic structure later, but quantum theory is about quantized energy levels. So here you have like a continuous energy, so really you can pick it. You can pick that energy level or that energy level or halfway in between or a quarter way. So you can pretty much pick any. That's what a continuous scale is. You can pick down to however many decimal places you want, kind of thing. Quantized energy levels means that you can only pick certain steps. This is like a ramp, this is like a set of steps. So electrons can only sit at specific energy levels in an atom. So they can sit at a ground state, n equals 1, or at higher energy states, n equals 2, n equals 3, n equals 4, up to n equals infinity, where they've sort of escaped the atom. So you can think of it as a bit like steps. So the ground state is the ground on Earth, and as you expend energy to go up by walking up steps, and if you walk up enough steps you're in space and you've escaped Earth's gravity. So same sort of thing for an atom analogously. This was discovered by looking at something called the photoelectric effect and also looking at spectroscopy. So electrons absorb the energy of light and get bumped up energy levels, and then when they go back down they release energy in the form of light or electromagnetic radiation, so sometimes infrared or UV or X-rays. And the energy change is equal to Planck's constant, h, times the frequency of the light that they emit. So it was noticed that elements can only emit certain wavelengths of light when excited, and they were creating spectrums of light that were like individual lines as opposed to continuous spectrums, which pointed towards quantized energy levels, as well as some experiments with the photoelectric effect, noticing they could only absorb certain wavelengths of light. And for an atom with only one electron, these energy levels can be mathematically predicted, and you don't have to know how this equation came up, but the energy at some energy level n is equal to negative Rydberg constant. The Rydberg constant is 2.18 times 10 to the minus 18 joules times the atomic number squared on the energy level that you're trying to calculate squared. So 1 is the ground state up to infinity. Notice that it's negative energy level, so it's like potential energy. That might not make so much sense to you, but you think of it as the energy goes up but goes towards zero as you get higher and higher. So you it's the amount of energy that you will regain when you fall from that level, if that makes any sense. So what's important here is that you can use that to predict what wavelengths of light will be released when certain hydrogen-like atoms, so atoms with only one electron, are excited, and their electrons jump between energy levels. What's important to note though is that you can't use this formula for any system that has more than one atom, more than one electron, because then you get electron-electron interactions, and they're not taken into account by this formula, and in fact they're pretty much impossible to predict. It becomes exceedingly complicated at that point, and it goes beyond the scope of first year chemistry. So you don't need to worry too much about calculating all of that because it's not too important, but we will do an example in a second. What's more important is to realize that because those energy levels sort of coincide with energy gaps, and therefore when you fall from different energy levels, that gives you different energies of light. So blue light or UV or anything, X-rays and stuff, are higher energy. So falling from a higher energy back down to the ground state will give you blue light. Falling from a lower energy level down to the ground state will give you red light, although it won't necessarily give you red light. Falling from the ground state of hydrogen to the ground state from the n equals 2 to n equals 1 of hydrogen is still in the UV range, because there's still a huge gap between n equals 2 and n equals 1. But if you fall from n equals 7 to n equals 6, then you might get red light. So smaller gaps lead to the release of lower energy photons, and larger gaps to the release of higher energy photons. And spectroscopy can be used to detect which elements and compounds are present, because spectral characteristics, so which wavelengths are absorbed and emitted, are specific to molecules and specific to atoms. So depending on how they're configured in terms of electrons, and in terms of what other molecules are around them what other atoms are around them in a molecule. So spectroscopy and looking at what is absorbed and emitted can be used as a type of molecular fingerprint. So just a quick example. So an electron transitions from n equals 4 to n equals 3 in lithium 2+. What wavelength photon does it release? So the change in energy is equal to the energy of step 4 of n equals 4 minus the energy of n equals 3 equals the negative Rydberg constant times 9, because it's z squared. So the atomic number of lithium is 3, so 3 squared is 9, times 1 on 4 squared minus 1 on 3 squared, which is 1 on 16 minus 1 on 9 equals 1 on 7. So the energy change it's releasing 2.8 times 10 to the minus 18 joules of energy. When you look at that in terms of the change in energy is equal to HV. So that's the equation we saw before, where H is Planck's constant. You can solve for the frequency being 4.23 times 10 to the 15 hertz. So that's very, very high frequency. And then if you use the speed of light equals the wavelength times the frequency, that's the same for every wave, you get 3 times 10 to the 8, which is the speed of light, on 4.23 times 10 to the 15. You get the wavelength is 70.9 nanometers, which puts it in the sort of UV X-ray part of the spectrum. So you can see that a lot of these electron transitions are actually not in the visible range, even though I was using blue and red light as an analogy. But some of them are, and that means that we can look at them and observe them, and those ones are, all of the electron transitions can be detected, and those spectral characteristics can be analyzed in terms of sort of detecting what molecule is there and detecting what kind of electron interactions and the electron transitions are going on.